Hello students, how are you all? So today we are going to discuss about a very important topic of organic chemistry, and that is the exceptional stability of CPM carbocation. You can also say CPM cation. So first of all, what is the meaning of CPM carbocation and why it has an exceptional stability? So today we are going to discuss this in very detail. So open up your notebook, first try to understand, then make your notes. Okay, so what is this? CPM. CPM cation. CPM cation. What is the meaning of C? C stands for cyclo. C stands for cyclo. P stands for what? Propyl. P stands for what? Propyl. And here this M, it stands for methyl. So this is cyclopropyl methyl cation, or you can also say cyclopropyl methyl carbocation. Okay, so let's make its structure. This is cyclopropane. This is cyclopropyl group, and now this is cyclopropyl methyl carbocation, CPM cation. Okay, so it has an exceptional stability. Okay, so if I compare this cyclopropyl methyl carbocation with benzyl carbocation, I hope you know about this one, benzyl carbocation, and we know one thing, that benzyl carbocation is stable due to resonance, due to delocalization of pi electrons. It is stable. This is what? Benzyl carbocation. Okay, and you will be wondered to know, you will be surprised to know that this cyclopropyl carbocation, it is even much stable, more stable than benzyl carbocation. What's the reason behind it? Okay, so to discuss this thing, to understand this thing in detail, let's draw the structure of this cyclopropane first. This is cyclopropane. Okay, so we have this carbon, CH2, CH2 and CH2. Okay, basically we tell students that in cyclopropane every carbon is sp3 hybridized. I hope you know about it. Every carbon is sp3 hybridized. But we know one thing also, that in sp3 hybridization, bond angle, ideal bond angle is 109 degree 28 minutes. So if this carbon is sp3 hybridized, then its bond angle, it should be 109 degree 28 minutes. But as we know that in cyclopropane, this bond angle is not 109 degree 28 minutes. It is much smaller than 109 degree 28 minutes, and that is 60 degree. Every angle here 60 degree. Okay, angle CCC in cyclopropane is 60 degree, which is much smaller than a regular sp3 hybrid angle, that is 109 degree 28 minutes. Okay, if the angle is much smaller, then there must be angle strain. There must be what? Angle strain. So in cyclopropane we observe what? Angle strain. So I'll tell you one thing. In cyclopropane there are two type of angles. One is interaxial angle. This 60 degree angle, it is known as what? Interaxial angle. Interaxial angle, theta. That is equal to what? 60 degree. But as I told you that there is an angle strain. So this bond, it just wants to open itself to a bit. Okay, to minimize the angle strain, to lower down the angle strain. Okay, so second type of angle in cyclopropane, that is known as what? Interorbital angle, or you can also say interorbital angle. Interorbital angle. Okay, so this carbon's orbital, hybrid orbital is like this. This carbon hybrid orbital is like this. Okay, so these are the orbitals. Okay, similarly this carbon's hybrid orbital is like this, and this one is like this, and they overlap each other. They overlap each other. Okay, so this angle, now this complete angle from here to here, this complete angle, it is between orbitals, hybrid orbitals, and that angle is known as what? Interorbital angle. And this interorbital angle in cyclopropane, that is equal to what? That is equal to 102 degree. That is equal to 102 degree. Due to angle strain, this angle will slightly open up. How much? 21 degree from this side, 21 degree from this side. Now the interorbital angle, it will become equal to 21 plus 60 plus 21, and that comes out to be what? 102 degree. Okay. So here interorbital angle is 102 degree. So the main thing, as I think you know, that in cyclopropane every carbon has two type of hybridization. One is sp5 hybridization and one is sp2 hybridization. There is not sp3 hybridization, which we usually tell our students that in cyclopropane carbon has sp3 hybridization, but it's wrong. In cyclopropane every carbon has two type of hybridization. One is sp5 and one is sp2. So I'll make another video based on sp5 hybridization some other day. Today we are going to discuss about cyclopropyl methyl carbocation stability, exceptional stability. Now the thing is that this angle, it is not purely sigma, neither purely sigma nor purely pi. This bond is between sigma and pi. We know that a sigma bond is formed by what? Direct overlapping. A pi bond is formed by what? Sideways overlapping. But this is neither direct overlapping nor purely sideways overlapping. This bond is between sigma and pi. So we can say that this bond is known as what? Bent bond or banana bond. A bent bond, it is weaker than sigma bond. And a bent bond is slightly stronger than pi bond. So now can I say one thing, that this bent bond, it has some sigma bond like character and some pi bond like character also, because it is between sigma and pi bonds. That's why it has obtained both of the characters, sigma bond character as well as pi bond character. Understood? No problem. Okay, now let's come to this cyclopropyl methyl carbocation. Okay, so what is the hybridized state of this carbon here? We have two hydrogens, two sigma bond here and one sigma bond here. Total 3. There is no lone pair. So only 3 sigma bonds are there. So the hybridized state of this carbon is what? sp2. Is what? sp2. And as we know that in sp2 hybridization only 2 p orbitals are used. 1 p orbital is left what? Vacant. So the p orbital which is left vacant, I am going to draw it. Suppose this is a p orbital, vacant p orbital. C, H, okay. So this is the vacant p orbital, suppose. Okay, I can make this hydrogen in wedge and this hydrogen in dash. Got it? This carbon has got what? Positive charge. And this is known as what? P orbital. P orbital, and that is what? Vacant. Okay. Now, we know that this bond is not purely sigma. It has got what? Some pi character also. Like this. Similarly, I can draw here like this. Here also. Now the thing is that if we study about the stability of carbocation, now these two electrons, the two electrons which are present here in this bent bond, now these are close to this vacant p orbital. These two electrons, they are close to this vacant p orbitals and they can go to this p orbital and they can provide stability to this carbocation. Similarly, they can also go from this side also. This side also. Previously, we know that this bond is like this, but actually, due to angle strain, this bond is not like this. This bond is like a bent bond. Now, these two electrons, they are close to the vacant p orbital. They can overlap with the vacant p orbital. They can go there. That's why it can provide stability to cyclopropyl carbocation. If I going to draw the structures, for example, suppose first what will happen? if these two electrons will go to this vacant p orbital, which kind of structure we'll get? We'll get a positive charge over here and a double bond over here. Okay, you can write CH2 or you cannot write CH2, no problem. Okay, so this is one of the resonating structures, you can say. One of the resonating structures. Okay, suppose structure number 1. If I going to draw the structure, if these two electrons they go here, so the another resonating structure can be like this one, positive charge over here, double. Yeah. So these two are the resonating structure, and if we draw the resonance hybrid actually, so there is no bond, there is a bond, it means from 0 to 1 it will be like this kind of bond. Okay, same here, this kind of bond. Okay, then this bond was single here, this bond is double here, it will be like between double and single, CH2. This carbon will get delta positive. Okay, this carbon will get delta positive, this carbon will get a delta positive. So this is the resonance hybrid of cyclopropyl methyl carbocation. So this cyclopropyl methyl carbocation, it gets stabilized by resonance, and that resonance is known as sigma bond resonance. That is known as what? Sigma bond resonance. These sigma electrons, because these electrons, this band bond, it has sigma bond character also, it has pi bond character also. These sigma electrons, they go to the vacant p orbital of this C positive, and they provide exceptional stability to this carbocation. That's why it is known as what? Sigma bond resonance. Why we say resonance? Because in resonance we know pi electrons participate. I told you earlier that this band bond, it has pi bond character also. So we can say these pi electrons are moving here. That's why we have given the word what? Resonance. Sigma bond resonance. Sometimes it seems like that these sigma electrons, they disturb the skeleton. They disturb the skeleton of this cyclopropyl carbocation. Like this. Sometimes they give electrons like here, sometimes like this. It seems like the carbocation, it is dancing. So sometimes we give it the name what? Dancing resonance. Dancing resonance. But I'll tell you one thing. We relate this one with dancing resonance, but there is no such term like dancing resonance. It seems like dancing. This carbocation is dancing. But there is no such term like dancing resonance. Better we say sigma bond resonance. Got it? Okay. So this cyclopropyl methyl carbocation, it gets extra stability due to sigma bond resonance. Understood? Okay. Now, if we see this benzyl carbocation, benzyl carbocation. So this benzyl carbocation, what we can see here? Only resonance. But in sigma resonance, what? Pi conjugation. But here we have sigma bond resonance, which is much powerful than this resonance. Okay. Suppose we have C positive, then this one more cyclopropyl ring, and one more. Suppose we have this carbocation, tricyclopropyl methyl carbocation. It is the world's most stable carbocation ever. What is this one? 3 cyclopropyl rings are attached to this one. This is known as what? Tricyclopropyl methyl carbocation. World's most stable carbocation ever. This is more stable than what? CH positive. Suppose there is one cyclopropyl ring, there is another ring. This is the dicyclopropyl methyl carbocation. Then what? Same cyclopropyl methyl carbocation, CH2 positive. And this cyclopropyl methyl carbocation, it is even much stronger than this one. I hope you know about this one. This is known as what? What? Tropylium cation. Tropylium cation. Tropylium cation. In tropylium cation, why tropylium cation is stable? Due to aromaticity, because it obeys Huckel rule. It obeys Huckel rule. So this is known as what? Quasi aromatic cation. It obeys 4n plus 2 pi electrons. 4n plus 2 pi electron rule. Okay. So the cyclopropyl methyl carbocation is even much stronger than tropylium carbocation also. Sometimes in exam they can give you a question like, suppose which among the following gives fast SN1 reaction, or you can say very quick SN1 reaction. We know the concept of SN1 reaction. Okay, so in SN1 reaction, it is about what? Stability of carbocation. It is about stability of a carbocation. Suppose if options are given to you, one of the option is suppose CH3 thrice CCl. Second option, suppose they will give you chlorobenzene. Third option, suppose they will give you benzyl chloride. And fourth option, suppose they will give you same CH2Cl. Okay, so SN1 reaction, what is the concept of SN1 reaction? It depends on the stability of carbocation, because the intermediate formed in SN1 is a carbocation, and the carbocation which is much stable, that will give SN1 reaction fast. If we remove this Cl negative ion from here, we'll get this positive. This is trimethyl. Okay, chalo. Tertiary butyl, you can also say tertiary butyl carbocation. If we remove Cl negative from here, we'll get what? Phenyl carbocation, which is least stable. Okay, if we remove Cl negative from here, we'll get what? Benzyl carbocation, stable. And if we remove Cl negative from here, we'll get what? CPM carbocation, which is exceptionally stable. So which will give quick SN1 reaction? Option number 4. And if we observe the order of these to give SN1 reaction, then that will be fourth one will give SN1 reaction very quickly. Followed by what? Now tell me, which is more stable? Tertiary butyl or benzyl carbocation? If you know about organic chemistry a bit, then I hope you know about that. This tertiary butyl carbocation, it is stable than benzyl carbocation. Why? Due to hyperconjugation. 9 hyperconjugative structures will be formed. Okay, so 4 followed by 1 followed by 3, and the least one is what? Option number 2. So they can ask you a question like this one. Similarly, they can give you a question like, suppose which among the following can give precipitate with AgNO3 quickly. Will give precipitate with AgNO3 quickly. I'm giving the options. Okay, first option same. Suppose CH2Cl, benzyl chloride. Second option same, CH3 thrice CCl. Third option, it is CH2Cl. And fourth option, suppose they will give you CH2 double bond CHCl, vinyl chloride. So the same concept is over there. Okay, so precipitate with AgNO3, it will give you Ag positive and it will get Cl negative from here. And after giving Cl negative, what will be formed? Carbocation. And the carbocation which is much stable, that will be formed first. That will give precipitate with AgNO3 quickly. Okay, so after removing this Cl negative, we'll get what? Benzyl chloride, benzyl carbocation. And here we'll get what? Tertiary carbocation. Here we get what? CPM carbocation. And here we have what? Vinyl carbocation. And we know that vinyl carbocation is least stable. So the most stable carbocation formed here is what? CPM carbocation. So this cyclopropyl methyl chloride, it will give precipitate with AgNO3 quickly. Okay, and if we compare the order, if we get the order of giving a quick precipitate with AgNO3, first it will be 3, then which is more stable, tertiary or benzyl? Tertiary. Then it will be 2, followed by 1, and the least stable one is number 4. So they can ask question like this one. So cyclopropyl methyl carbocation, CPM carbocation, it has an exceptional stability due to sigma bond resonance, and sometimes we refer it as dancing resonance, which is not correct actually, because there is no such term like dancing resonance, but it seems like dancing, that's why we say dancing resonance. I hope you have understood this topic very clearly. So we'll see in another topic. Till then, thank you.